In 1967, graduate student Jocelyn Bell Burnell discovered a radio signal from space. For a brief moment, she and her advisor thought they had encountered an alien civilization. But what was it really? I'm Miss Paws, and today we're going to talk all about pulsars. What are pulsars? When a massive red supergiant star exhausts its fuel and collapses, a supernova explosion, the largest explosion in space, takes place. At the center or the core of the dying star, positively charged protons and negatively charged electrons are crushed together to form densely packed neutrally charged neutrons. Containing 1.4 of the Sun's mass squeezed into the size of a city on Earth, these densely packed neutrons, or neutron stars as we like to call them, are the densest objects in the universe. One type of neutron star that is rapidly rotating, highly magnetized, and emits electromagnetic radiation is a pulsar. When a star collapses and rapidly shrinks, it still retains its mass. In order to conserve angular momentum, the star starts spinning quickly. This is much like an ice skater that pulls their arms inside. At the surface of the neutron star, the neutrons decay into protons and electrons, which enter incredibly strong magnetic fields and rotate along with the neutron star. These accelerated protons and electrons can only escape this magnetic field at the magnetic poles of the pulsar. As the particles are released from the field into narrow beams from the magnetic poles, they give off electromagnetic radiation almost in a similar manner to a lighthouse. While most pulsars emit radio waves, some pulsars have been discovered to emit other types of radiation, such as visible light, X-ray, or gamma-ray wavelengths. Pulsars emitting visible light appear as a flickering star to astronomers. As the neutron star rotates, we observe pulses only when the magnetic poles align with Earth, as the magnetic poles of the pulsar are not in the same spot as the rotational poles. The discovery of pulsars was exciting and eventful. It started when in the mid-1960s, a PhD student, Jocelyn Bell, joined her advisor, Anthony Hewish, in a project to observe quasars, bright objects in space that give out powerful radio waves. For 2 years, Bell and her lab mates built a radio telescope that would detect radio waves by scanning the sky in order to observe quasars. In 1967, the construction of the telescope was finally complete. After a few weeks of operating the telescope and analyzing data that the telescope had outputted on chart paper, Bell noticed something odd. To quote the discoverer herself, "One day I was looking for quasars, and there was a signal I couldn't explain. It wasn't a quasar, and it didn't look like any kind of interference that I had seen before." Upon further inspection, Bell realized there was a regular pulse on the chart coming from the same patch of the sky. When she brought this up with Hewish, he deemed it was just interference, that it could be unwanted radio signals from other sources, and perhaps the telescope was wired up incorrectly. But as they slowly ruled out all potential sources of interference, such as television signals, orbiting satellites, and a metal building near the telescope, the researchers were convinced that this was something amazing. The researchers named this new source Little Green Men and wondered if aliens were the source of this signal. But when Bell discovered another pulse similar to the pulse that she had seen before in a different patch of space, she ruled out extraterrestrial aliens. Likely, there were not two groups of aliens communicating "we come in peace" to Earthlings. Bell had just discovered the first two pulsars. Eventually, when the discovery of pulsars was announced, the popular press asked Anthony Hewish about the significance of this discovery. But what about Bell? Well, they asked her about her measurements and dating life, regarding her merely as a little girl. It was unfortunate that she was not taken seriously in the scientific community solely because she was a woman. In her science classes growing up, Belle had been the only girl, or one of very few, in a classroom full of boys. As an undergraduate student, the male students would whistle at her and beat their hands and feet on the floors and the desk. Many of Belle's classmates thought she would stop pursuing physics and switch majors, as many women before her had done. However, she stuck to it. When she got to Cambridge to do her PhD, she suffered from imposter syndrome, this feeling that she didn't belong, since many of her male classmates and professors looked down on her. So Belle made sure to work her very hardest. She spent hours in lectures, and in the evening she analyzed data outputted by the telescope, not using a computer, but by hand, going through 96 feet of chart paper each day, distinguishing cosmic signals from interference. Despite all her hard work, in 1974 the Nobel Prize in Physics was awarded for the discovery of pulsars to Belle Burnell's advisor Anthony Hewish and the head of the Cambridge Astronomy Group, Martin Ryle. One would think that Belle Burnell would have been included in the Nobel Prize for the discovery of pulsars, since their collective effort made the discovery possible. The counter-arguments Professor Belle Burnell made herself in 1977 are: it is the supervisor who has the final responsibility for the success or failure of the project. It seems only fair to me that he should benefit from the successes too. I believe it would demean Nobel Prizes if they were awarded to research students except in very exceptional cases, and I do not believe this is one of them. But that was from 1977. In a recent video with New York Times in 2021, Professor Belle Burnell says, "I think the fact that I was a graduate student and a woman together demoted my standing in terms of receiving a Nobel Prize." In 2018, Professor Jocelyn Bell Burnell received a special breakthrough prize in fundamental physics for fundamental contributions to the discovery of pulsars and a lifetime of inspiring leadership in the scientific community. She donated the entire $3 million award money to the Institute of Physics to fund scholarships for underrepresented physics PhD students. "I think diversity makes the subject stronger," she says.
Thank you for this very great honor. And thank you for doing me the honor of being here this evening. I plan to use the money that's been awarded to me to create research studentships in physics for people from underrepresented groups in physics.
And by the way, discovering pulsars was not the only thing that she did. Professor Belle Burnell went on to research gamma-ray astronomy and has become a very versatile astronomer. Since the discovery of the first two pulsars, we know a lot more about pulsars. The two main types of pulsars are ordinary pulsars and millisecond pulsars. The majority of pulsars, ordinary pulsars, spin at a rate of about once per second. Millisecond pulsars, on the other hand, spin faster than 50 milliseconds and are generally the oldest known pulsars. Now, if you think pulsars are cute and non-threatening, you would be wrong. Some of them can eat their companion even when they are dead. As pulsars get older, they slow down and eventually stop emitting radiation, or at least enough for our telescopes to detect. They reach a stage in their life which we call a pulsar graveyard. However, if there is a stellar object near this dying pulsar, it sucks the energy and material from that object. The sudden change in material and energy exponentially increases its spin to create a millisecond pulsar, which is why millisecond pulsars are sometimes referred to as recycled pulsars. Scientists are using pulsars to study how matter behaves in the most extreme conditions, since pulsars are the densest objects in space and have very strong magnetic fields. The spin rate of pulsars, and thus their pulse of radio emissions, is so precise that pulsars are considered the most accurate atomic clocks in the universe. Thus, any aberrance in these precise pulses can reveal interesting secrets of the universe. For example, binary pulsars, or pulsar in orbit around another pulsar, can be used to test theories such as Albert Einstein's general relativity and study gravitational waves, invisible and fast ripples in space-time that can stretch and squeeze anything in their path. In his general theory of relativity, Einstein predicted that gravitational waves are caused by massive accelerating objects orbiting around each other. The two pulsars in orbit around each other start losing energy as they emit gravitational waves, affecting the timing of the pulses. Similarly, pulsars can also be used to weigh planets and asteroids. Due to Earth's orbit around the Sun, the time it takes for a pulsar's radio signal differs slightly from period to period. In order to make sure the pulses are consistent, scientists recalculate the time it takes for the signal to arrive to a common reference frame, the center of mass of the entire solar system, or the solar system barycenter. As the planets move around the Sun, the barycenter also shifts. The barycenter at any given time is calculated using the locations and the masses of the planets. If the masses of the planets have been incorrectly calculated, there will be timing errors in the pulsar data. By correcting the masses of the planets, the error will disappear. Most space vehicles, no, not in Star Wars, but in the real world, rely heavily on Earth-based navigation, which has limited scope because of service interruptions. As the cost of vehicle operations continues to increase, spacecraft navigation is evolving toward autonomous celestial-based systems. Pulsar navigation can contribute to that autonomous celestial-based system, since pulsars emit periodic signals that can be used to calculate the position of the spacecraft. As a student, Belle Burnell had analyzed data outputted by the telescope by hand and had learned to recognize what radio signals came from pulsars and what were just interference. In the years since, pulsar research has dramatically increased, as has the volume of the data to be analyzed. Extremely high sensitivity radio telescopes, for example, can capture billions or more of pulsar candidates. Analyzing all the data outputted by the telescope by hand to determine which signals are coming from pulsars is just not feasible. So the question is, how can we make distinguishing radio signals of pulsars from other radio signals easier for us? Pulsar candidates can be classified efficiently as pulsar or not pulsar by machine learning models. In fact, such models can classify over 1 million candidates per day. But let's not get ahead of ourselves, that's a topic for a separate video. The discovery of pulsars was a breakthrough and led to developments in other fields as well. If you want to learn more about other major breakthroughs in STEM, make sure to subscribe to this channel.